No, probably like this is better. Okay. Um, so a little bit about me and my motivation. So I wanted to understand the brain, right? How best to understand myself and is how do I process? Because this is everything that's about us. And so from very early on, I went about that to study every aspect of the brain and everything that touches on the brain. And I think one of the more important things I studied is electrical engineering and computer science, but electrical engineering because I wanted to get the basis of the electrical signalings and the tools to study the neuroscience. So how do you know how good the tools that you're using to do like electrophysiology experiments and so on, without really understanding the electronics and the limits of the electronics there. And then in part of that process, electrical engineering studies a lot of feedback and dynamic systems and so on. So it provides a lot of tools, computational tools, to understand the dynamics and estimate and so on. So I I did that, and then I did a PhD in computational neuroscience, actually going into the labs, doing the electrophysiology experiments, playing with all the knobs and the noises and the non-reliabilities. And I also felt like it's important. So neuroscience, the neurophysiology experiments can tell you, if you put an electrode on a cell, so you know what that neuron is doing, but you don't know what the rest of the circuit is doing. And the chance of taking another electrode and getting it exactly on the circuit, because the brain is so dense, is very low. So you get incomplete information, even though you're recording there, you get very incomplete information. And even if the neuron is not directly on, the electrode is not directly on the neuron, so you get a few, maybe tens or hundreds of neurons, still you don't know what the rest of the circuit is doing. And fMRI and MRI will tell you more of what thousands of neurons, tens of thousands or hundreds of thousands of neurons. It's not going to tell you what the circuit is. And EEGs are similar. They'll give you a very good time domain of what's going on with the neurons, but then it's a sum of hundreds or millions of neurons all activating at once. So none of these recording methods are exactly telling you what the circuit's doing. And then I also, in my computational neuroscience, I worked in cognitive psychology labs as well to do experiments there, to understand eye tracking, to understand reaction times, what sort of patterns are easier for us to process or less easy for us to process. That then gives information about how the circuits are functioning. And my idea, along with getting an MD focusing on neurology, is to try to find the a theoretical circuit that you can simulate and get results that matches as many of the phenomena that you see from many of these fields as possible in order to find the best match of it. And of course, computer science provides you the tools to actually analyze the algorithms and analyze, how recognition is done and so on, and compare with different algorithms. So I think it's very important when approaching some of these questions is approaching it with a multidisciplinary background. But unfortunately, I don't think academia is optimal for that. There is so much politics for each separate field that if you then try to combine many fields, it just multiplies on itself. So actually how science is done today is not through this sort of philosophy. And I think that really hurts us a lot. So ultimately, what I decided to do is to open up my own startup company, Optimizing Mind, and to actually take that algorithm and then use it to where businesses or customers may need it the most, um, in training algorithms, in understanding the environment, and so on. And that's what I will talk about here. So we've been actually funded by the National Science Foundation for small business and so on, but it's not. We want to open up and capture more and more customers. So going back to the science, the brain utilizes feedback in ways that current AI does not. It just simply does not. Um, and our goal is to achieve a more human level recognition and learning. So current AI, which has been around since the 1940s and 50s, is based on feed forward recognition. And that is, you take the inputs, you multiply by the weights that you've learned, and you get an output. So the direction is from the inputs all the way to the outputs. And that's the core of recognition, and that's the core of the algorithms. And the hard part is then learning to find the right set of weights, and that turns out to be very difficult in current technology. But so when you contrast this, when it's feed forward, information just goes from the inputs to the outputs when you do recognition. And then you look at the brain has feedback throughout of it, throughout sensory organs like the thalamus and the cortex, where information will go into the eyes to the thalamus and the LGN, go to the cortex, and then the cortex will feed back to the LGN, and that will change the information that is going through the LGN, which will then affect again what's coming out of the cortex. So there's a lot of this feedback, and there's feedback in the cortex as well. And you see these in neuron connections. These are neuron connections of the LGN. You also see this in specific neuron synapses, where you see these trisynaptic synapses where information will actually go down the backwards and then affect the modulating axon and dendrite, which then will affect the receptivity of the dendrite going up. And there is also a retrograde signaling such as nitric oxide, which is available everywhere. So some scientists say that or most neuroscientists say that there's more feedback than feed-forward connection in the brain. And you see evidence of this all over the place. If you take a set of neurons, one presynaptic, one postsynaptic, one neuron that is sending a signal and one neuron that's receiving the signal, then you see that they are adjusted. And that's this homeostatic plasticity. So if you activate the presynaptic neuron, you'll get a postsynaptic neuron response, right? But if you increase the frequency, so you somehow either increase the frequency of your stimulation, or you change through chemical compounds how effective the receptors are, then you'll notice over time the strength of this connection from the presynapse to the postsynapse decreases. And that decreases at this neuron that is sending the signal. So that means the output neuron, that means the input neuron knows what the output neuron is doing. And Similarly, if you change the frequency the other way, you see an increase in the size. So there's this normalization function throughout the brain where the neurons are adjusting for themselves with feedback. This is everywhere. And this is wholesalely ignored with the with the type of networks you have today, especially during recognition. And so the type of model that I worked on are models which have that sort of feedback back to the input. And I ask, what do they do in real time? And so these are feedback during recognition. So instead of recognition being X input, which is X times weights equals outputs Y, that process during recognition incorporates feedback. And so instead of the feed forward input to output, you have inputs. The neuron that sends the input knows something that happens from the output neuron, and they feed back and talk to each other and we ask, well, what is the function that they do, right? And this is completely aligned with other phenomena that you see in the brain, such as excitation, inhibition, balance, and so on, which I didn't put in these slides, I don't believe, because I want it to be shorter. But if anybody has questions and wants to see some of these phenomena, I can pull out the slide. I have a whole set of slides that I've given to I've had talks with postdocs over at Berkeley and so on. So I have all the slides there. So kind of the core of things is, does the brain recognize like AI? The brain recognition is faster with unique patterns, kind of like solving a jigsaw puzzle. So if you solve a jigsaw puzzle like this and you have all the pieces and you're trying to put them together and understand the scene, certain pieces are going to give you more information and be quicker to put together than other pieces, right? And that's a signal to noise type of ratio in the processing. Now, in AI recognition, which uses feed forward, it always takes a fixed amount of time, y equal wx. So you wouldn't have these differences in the pieces. And now I'm going to do a test for you guys in the audience in case you're dozing off. So your goal here is to find the unique pattern that's going to pop up on the screen. And what you want to do is just, internally estimate how long did it take for you to recognize the single pattern in this square. So ready? Here we go. It's the X, and you recognize the X. Now I'm going to give you another set of patterns. Ready? Here you go. Here's the pattern. Now the unique pattern in the second one is the F. Now, because of the interactions and the feedback, they take longer and different. And this is a signal to noise type of phenomena like the jigsaw puzzle. And it happens everywhere, even if you don't see space, right? In olfaction, in smell, you see this phenomena. Smell isn't as good at processing space. You see it in sound and in touch and so on. So it occurs in all senses. So this is a fundamental part of the circuitry that's doing recognition, but it's not accounted for by the AI. So current AI and the brain recognize very differently. Now, this ties back to the problems that you see with the current AI. So the brain and the AI, they both can do learning and both can do recognition or inference. Right? So let's talk a little bit about the current AI. So we already said for recognition inference, current AI is using this feed forward in order to do the recognition. And in order to do that, everything is in the weights. And so weights have to be learned in a form that the recognition occurs within one multiplication, right? And that's not a simple thing. What you have to do is to optimize all the data set to make sure you're not missing anything and predict the whole real world environment in order to get this to work. And this is pretty much all the algorithms that you have out there: deep, convolutional, recurrent, LSTM, reinforcement, so on. Even in their if in their name they have like recurrent, which implies some sort of feedback, it's not exactly feedback on this in the form that I'm talking about. It's feedback in time to capture time sequences. It's not true feedback, because the current algorithms are all based on this y is equal to wx, right? So pretty much everything that is out there today, and all the funding and so on, is based on this sort of algorithm, and that takes the lion's share. But the problem is with this feed-forward algorithm, number one, weights are a black box. Because they're optimized for the whole data set, you can't tell, what is the brain looking for when it's trying to look for a specific pattern. And the second problem is that optimizing over the training data, the whole training data, you have to have the whole training data there present ahead of time, and it's computationally intensive, right? This is why you need the big servers, and it takes months for Google to learn the big LLM models and so on, with more data than a human can ever consume in their lifetime. But even worse, for any update of the training, you want to add one new word or one new category or one new image. You're going to learn elephants now, right? Training has to be updated from the beginning, and you have to do the optimization on all the data sets and everything that you've previously known in order to create a new feed-forward network that'll now have this new data. Okay? And so part of this problem is that these feed-forward weights are encoding uniqueness into the weights in order to be able to do this one forward multiplication. And so to give you an indication of how this encoding is going in the traditional network, let's say you have a training instance of Q's and O's. In the traditional method, you're optimizing weights to recognize Q. So in this training example, the diagonal is going to be important because that's the signal that's unique. So then the weights are increased for the diagonal features and decreased for the circular. Now in another training instance, you might have Q's within X's. Well, the unique features here are the circle. And that's important. So then it goes through the whole data sets and adjusts the weights for all the features in the data sets, and you need the whole data set. But the reality is you cannot learn uniqueness for all possible contexts. You can't predict the whole world ahead of time, and you don't have data for the whole real world ahead of time. And so the question is this the best strategy? Moreover, in certain environments or certain examples, if you learn, for example, stripes are the most important thing for zebra, and you're given this image, that's not going to help you recognize so much. It's more the horse-like features of zebra that's going to help you recognize zebra than the stripe feature. So context during recognition is very important. And it's during the recognition, not during learning. So the idea is that the uniqueness is determined during recognition instead, when the context is available, and it's using this feedback. And that feedback is then doing optimization during recognition. It's going back and forth between the output neuron and the input neuron, back and forth, and evaluating what is the most likely thing. And in this process, it's determining the outputs of the neurons, not the weights. So this is going back and forth between the input and output, and it's determining what is the most likely output based on everything you've learned before. And you're optimizing only on the current test pattern, not the whole training data. So that reduces the amount of processing that is needed and reducing the computational costs. This now allows you to learn expected patterns without uniqueness. You don't have to balance the whole, everything that might be in the data set. All you need to do is learn that a horse has 4 legs, zebra has 4 legs, it has a head, and whatever it is, you're learning it specifically for zebra. You don't care when you're learning zebra, you don't care if you know any other 4-legged animal or non-4-legged animal or anything else. You're just learning it for the zebra. So then the weights become in the form that's not a black box because it's oriented towards what is being recognized. Okay? So this now goes back to what's going on in the market with the current AI. So, for example, markets and markets. The biggest problem for AI development is obtaining the vast anonymized data and obtaining qualified experts that have to balance all the data and rehearse it and to get all the GPUs running right and so on in order to learn that W that you can multiply in one step. Right? And then it also affects understanding the decisions. You don't understand why the network does something wrong, and yet it's really hard to explain, why it did it. So what we do is using algorithms with feedback, we are number one able to train with much less data and are easier to update. And then we can give more rationales for decisions. I can go over that later. I'm not going to focus on that anymore. What I'm going to focus here for us is towards how this can affect businesses and learning and AI algorithms. So to do this demonstration of why this feedback is important, what we took is transfer learning paradigm. Now, Google has a TensorFlow, which is a package to train AI, and they have a tutorial. And what transfer learning does is it says, okay, let's freeze the bottom layers of training, make them fixed, and only train the top layer. So the idea is if you've trained a network and with natural images, so then it will already kind of know natural images. Now you want to train cats, dogs, birds, what have you. All you need to do is train the top layer. The bottom has captured most of the statistics of the environment, and what this transfer learning does is train the top layers. Now, this is a shortcut. It's meant to make training faster in current algorithms, so smaller companies can do it and so on. But even then, it's very, very difficult. And I will show you a demonstration. So, firstly, the transfer learning, the regular transfer learning in the TensorFlow tutorial, which is using the algorithm to learn the weights, I'm going to label as TL. And so since this is the gold standard, it's gold color, and it's TensorFlow is this color. So it's a gold standard. But this represents pretty much all the algorithms that are used today. They might change how quick it goes down the gradient and so on, but it doesn't change the fact that it needs so much data and so on. And now this tutorial, what it does is it takes images of cats and dogs and it trains it. So it takes a network that's previously a base layer that's previously learned on ImageNet, which has thousands of images. It freezes the bottom. and then it trains the top layer for cats and dogs images. And I will compare it with optimizing mind solution, which is using that feedback, which we're going to call transfer learning squared, because you'll see you can update both. You can update as you go along the top layer, as well as like you would do transfer learning. So it's as if you can do transfer learning twice. And so that's why we're calling it transfer learning squared. Now we're going to do benchmarks against both of them using the exact same data and samples. So both algorithms get the exact same data and the exact same number of data. So here you have what's called a learning curve. And this is purely the TensorFlow traditional algorithm being trained and run. So initially, it's not trained. It doesn't know anything about cats and dogs. Here is the sample number of cats and dogs when it's training. So there's about there's 1,000 images of cats and 1,000 images of dogs in this, and this is running the traditional one 30 times. So because it's running 30 times, you can see an average and the deviations, between them. And each training sample number is a pattern that the algorithm is given. And then you see how well the algorithm is doing. You do this validation. There's a set of cats and dog images that are not in the training set that are used to determine the accuracy of the algorithm. Right? And that's how you get this curve. And what this curve is showing you, initially, the network doesn't know much. It's at 50%. But then over time, as it's trained, it does up to like 97% correct, answering all the cats and dogs. Okay, so this is the traditional algorithm, and this is the blue is a transfer learning square. It's the algorithm based on feedback. So what it's learning is much simpler data, and it's doing more of the computation for the recognition. And you see, it learns much quicker to get to this 97% correct. And I can zoom to the first 20 samples. So basically, this is right at the beginning of this graph. Okay, and you can see within 20 samples, you get a result that would have taken about 2,000 samples in the other algorithm. So it's able to learn much faster and get to that performance much easier that way, because it's not optimizing through all the data samples. So it's one thing to show this with two pieces of two categories, cats and dogs. It's much more important to be able to do many. So what we did is we expanded this to 50 animal types. So lions and tigers and bears and flower and bees and all sorts of stuff like that. So actually no flowers, just bees and insects and all monkeys and bears and so on and so forth. So this is the graph now redone with this 50 animal types. And now you can see it takes much more samples to get to the performance. But you see it didn't achieve as high of a performance. And again, you see the same curve. And you can zoom it into the first 400 samples, and you can see it learning. Now, this darker line is before all the animals were presented at least once. The light blue lines is they've been at least presented once. And this is showing you the curve, but now the same curve with the same 1% of samples, 100%, 100 times faster, just because you had to see 100 times less samples. And that doesn't even include the fact that you don't have to do the optimization. So that's even a simpler learning. And you get this performance around at 400, right? So you can see through these curves which algorithm is doing better and how. Now, one of the key problems that humans solve that current algorithms don't, which is why you need to rehearse all the data at once, is called catastrophic forgetting. So let's go back to our cats and dogs example. If I had taken all the cats that I have and trained them at once, then trained all the dogs that I have at once, what's going to happen with current algorithms? It'll eventually forget the cats after it trained the dogs. If you don't interleave the cats with the dogs, or in the bigger animal data sets, all the animals together at once, the current algorithms are going to forget them. And that's what we're going to demonstrate now. We're going to take the networks that have learned cats and dogs, and we're going to now train them only on birds, never repeating cats and dogs again, only birds. And so now your validation here is cats, dogs, and birds. So both the networks have been trained on cats and dogs. None of them know birds. So they only know 2/3, and so on. Now, when you run the training on only birds, what happens is the traditional algorithm will start learning birds, but at the same time forget the cats and dogs because they're not being rehearsed. And that's the catastrophic forgetting. It forgot the cats and dogs until you, at the end, only know birds and you don't know cats and dogs anymore. Now, giving the exact same samples to the algorithm with the feedback, it remembers the cats and dogs and just adds birds, and it's happy. There's no problem with that. So that means as an animal, as a human, you can learn, I can pull out something new and learn it just as I go in the real live environment and just add that to the network. But you can never really build an current AI system that can do that. You would have to retrain it all. And this is also why you can't have robots in your house and stuff like that, because there's things that are unpredictable. Your house is unique to yourself. You can't train for every environment. And so you can't update that robot for your house because it would take too long and every house would be different and so on. So this is why, you don't see Jetsons like robots running around. But this allows brain-like updating and editing, and that's what Optimizing Mind is doing. We have an API where we basically can give customers the ability to take their own data and their own base layers. We want to give as much of the data and the processing to the customer themselves. What they do is send to our API the information that goes through to the first to the bottom layers, then send the labels, that information and the labels to our API. And our API sends back a network that they can then use as they would use traditionally, but it's with the less data samples and so on, and all the benefits that you get in our form. And so to summarize, this sort of paradigm can save data scientists time, labeling of data. You don't need as much data. Unbalanced data is okay. If you have one cat and 100 dogs, that is still going to be okay. Or one saber-toothed tiger and thousands of cats. that's not going to be as much of a problem for this type of algorithm. But with current algorithms, you have to balance them. So you have to make fake data or something that causes errors. You have less rehearsing, shorter development time, faster turnaround, and more productive experience with the AI. So that's the primary offering for optimizing mind. And so our goal is easier to create and evaluate and update AI that's easier to create, update, and evaluate. So with that, I will stop here.
You know what? I like. Well, the first question when I was looking at it, I was like, "Oh my gosh, there's such a huge practical application." And you mentioned only one of them. Like you mentioned only like robots and the importance of the ability to train them faster.
Yeah.
What do you think? You are you selling it as so? What are you like? Offering, like in terms of like business offering, are you like providing customized solution, or it's something that simply like how does it work, how you work with the businesses? Can you please explain? For me it was not clear completely.
Okay. So basically, so a lot of the current, development of AI is kind of hard for small companies, right? Bigger ones, it's okay, but harder ones, it's not. And basically, all of the big companies, NVIDIA, Microsoft, AWS, they offer AI as a service where a customer can take a bunch of images and then transfer it to their systems, and their systems are going to do all the training for it, produce an AI for the customer, and then the customer can use that AI for what they need. So ideally we're offering for platform providers a way to accelerate that process, right? So we're not looking to work so much for customers that don't exactly know what data they have and what they do. We want to be more on the level of our target customer is more on the level of a platform maker, and then we can update the platforms for the platforms, update the AI for their customers much faster and easier. We can train it faster and we can update it faster. And a lot of these platforms are doing the transfer learning.
And there's any limitations? Do you have any like restrictions technology wise? Is there any limitation?
So currently in this form, we are doing transfer learning with the fixed layer on the bottom. It's part of convolutions and the way back propagation is and so on. We are working on, so there's a newer way of doing the bottom layers through transformers, and that's actually more conducive to learning in our form. So we're working on that. So currently, our project is to get our goals are to add our type of learning into transformers, which would be the bottom layers, which are showing that they are much more robust than the type of convolutions that have been used in the past.
Yes, so it's basically brand new approach.
Yes.
And there are tons of applications. I mean, pretty much any industry can use it.
Yes.
Yeah,
we're trying not to boil the ocean.
Yeah.
And focus on who has the most pain and who has the most resources to use this. So that's how we settled on to this sort of platform, the training and so on. But we can do other offerings like more explainability and so on. It's where the biggest pain point and the customers.
Understood. It's clear, and that's very interesting. Thank you so much for sharing. Anyhow, due to the time confusion, some of our speakers were thinking that we on ECT, but we're actually Pacific time, and they join us from all over the world. We have people coming from Dubai and from Jerusalem. And the thing is, we have to wait for them. So we have to make a break and wait for other speakers.
I think we can call this a lunch break.
Yes, let's do. Yes, let's do. Give me a second. Let's do. We got a question from the audience, from the Ronald Lopez. Did you see it?
Yeah. Yes. What customers? So are the customers that we're looking for. So we can either work with companies that are doing a lot of their own training that will need to kind of retrain and retrain and retrain, or the platform. Our target is the platform customers. But we believe that ultimately we can help everybody with this. And so our current target is the platforms, but we are hopefully over time going to expand to everything, because I believe at some point that the AI will be functioning more like the way we have it than the way it's currently functioning. What's limiting now is kind of what's the best demonstration, what's the best pain point. It's more of a business type of introduction and penetration than algorithmic wise.
Yes, Ronald, we hope we answered your question. Anyhow, it was very interesting and helpful, especially, for me, I'm always trying to learn new about, current methods of analyzation of data. Anyhow, we definitely have to meet again, because we have to keep networking, engaged, have more people coming. Anyhow, we definitely will meet again with Dr. Tsvi soon on the platform. Please keep in touch with us. And we are going to have a lunch break, and we will get back at 2 p.m. And we will have amazing speakers from different parts of the world, and they have their own innovations. Please stay tuned. I will see you at 2 p.m. Okay?
All right, great.